Hi, I'm Neil and I'm presenting a generative adversarial approach to formal registration and template estimation. Templates, or atlases, are barycentric representations of a set of geometric observations. Given images of a population, a template of the data is crucial to standard processing pipelines and is commonly found via alternating between iterative registrations and averaging of aligned images. This has applications including quantifying geometric dissimilarity from the center of the population and for performing template segmentation and deforming it to the input images. Given aging cohorts with subgroups of interest, analysis may require templates conditioned on age, disease, and other covariates. Usually, this is tackled via methods where aligned pre-selected images undergo temporally weighted averaging. Recently proposed deep networks for template estimation do away with the averaging and consider the template as a grid of free parameters jointly trained alongside a registration network and eventually converging to an unconditional template. Such methods can further estimate conditional templates by using a decoder to synthesize a template conditioned on an attribute of interest. However, existing iterative or deep network-based work optimizes registration objectives only regularized to be smooth without considering the realism of the deformations. As brain topology shows high variability, methods using only smoothness regularized losses and/or averaging may lead to the obfuscation of critical structural detail or lead to neuroanatomically implausible results. Practical conditional template building is even more challenging, as modeling choices may be quite specific to the target dataset. Data may arrive at irregular intervals, and it may show rapid morphological and appearance changes. Even conditional deep networks designed for such use cases may not capture the full variability of the underlying populations. Stepping back is worth considering what we want. We want template construction via realistic deformations, we want sharpness for easy anatomical delineation, we want accurate subpopulation modeling, and we want a method that doesn't have to be redesigned for each new dataset. We contend that these characteristics can be achieved via a generative adversarial approach. So, do we just use a discriminator to encourage realistic synthesized templates? No, because the support of the distribution of templates is much narrower than that of the entire population. We instead encourage realism in the deformed templates, such that their fidelity propagates back to the originals, while also regularizing the registration. However, that's not the full story either. We know that GANs are stable when trained on small images with lots of data and high batch sizes. However, neuroimaging really has none of that. Our images are large 3D volumes, real-world MR datasets are often limited to a few hundred samples, and current GPUs cannot fit the large 3D batch sizes and networks required for better training. We tackle these challenges via carefully designed networks for template generation, registration, and discrimination. The template generator linearly transforms its internal representations based on a jointly learned conditioned embedding, with this approach being more powerful and parameter efficient than previous attempts. A network then registers a synthesized template to observations via diffeomorphisms, with the registration of objectives regularized to be smooth and central to the entire dataset. We further develop discriminator conditioning mechanisms for simultaneous continuous and categorical attribute conditioning, and develop an extensive training stability pipeline crucial to the success of this method. For further detail, please see the paper. We build age and disease condition templates on the PREDICT-HD dataset, which longitudinally images controls and subjects with the Huntington's disease genetic mutation. We further build age condition templates on DHCP, which consists of both preterm and term-born infants cross-sectionally imaged from 29 to 45 weeks post-menstrual age. Our synthesized unconditional templates yield sharper and more interpretable structure, especially in the cortex, with more neuroanatomically representative structure as shown on the right. Conditionally, the synthesized templates faithfully capture the process of neurodevelopment. In comparison to foundational work, the new conditioning mechanism and adversarial losses enable capturing the full variability of the underlying dataset. As our synthesized templates are anatomically closer to the target images, they undergo much lower deformations to match the target, as indicated by the deformation norms given on the right. Quantitatively, our conditioning architectures, as shown in green and red, follow structural trends present in the population to a closer extent. As a result, they require lower deformations to the targets, showing improved centrality. For more quantification, please see the paper. Finally, in age and disease state condition synthesis, the presented method demonstrates stronger aging effects and group differences, and thus better represents the data. In conclusion, we presented a generative synthesis approach to template construction and registration. This enables training on data modalities typically difficult for GAN training, and leads to results which are sharp, anatomically representative, and easy to interpret and label. Finally, the presented framework is shown to work without changes on very different populations, which was not previously possible. Thank you for listening. Our code can be found at this link.